everyone, this is a video for class 12 of PH 125, and today we're going to be starting on Newton's third law, which will lead us into a discussion of contact forces and the normal force. Okay, so let's do a brief review of Newton's first and second laws, which are the laws that we've already talked about in the last lecture. So remember, Newton's first law tells us that if there's no net force acting on an object, then its velocity will be constant, or in other words, remember, constant velocity means zero acceleration. So the object will not accelerate if the net force acting on it is zero. All right, then similarly, Newton's second law tells us that if there is a net force acting on an object, then it will accelerate. So specifically, we learned from Newton's second law that the net acceleration of an object, which is just like the overall acceleration of the object that you would measure if you were actually standing there with a timer measuring the rate of change of velocity of the object, the net acceleration of the object is going to be the net force acting on the object divided by the mass of the object. Okay, I'll just remind you, the net force is just the vector sum of all the forces acting on the object. So we have to remember how to do vector sums. And so what we're going to want to do here is think about breaking our forces up into x and y components and adding them together to get the net force in the x direction and to get the net force in the y direction. Okay, and so then it turns out that Newton's second law, it holds in terms of components as well. And so something really useful to use in problem solving is to think about the net force acting in the x direction by summing up the x components of all the forces acting on your object and then setting that equal to the mass of your object times its net acceleration in the x direction. And then you'll want to do a similar process with the y components of all the forces acting on your object. Add those guys all up to get the net force in the y direction and then set it equal to the mass of your object times its net acceleration in the y direction. So this is really how you're going to want to go about problem solving using Newton's second law. Okay, and so to do that, you're going to have to determine the net force acting on an object. Specifically, you're going to have to determine the component of the net force in the x direction and the component of the net force in the y direction. And so to do that, it's really useful to draw something called a free body diagram. Okay, so we did do this last time, but we'll just go over it briefly again, and then we're going to do an example. So first step, really in any physics problem, when you read the prompt, you want to make a little sketch that helps you visualize what's happening in the problem. So I always recommend doing that. And then as far as actually drawing the free body diagram is concerned, you want to take your object of interest, so the thing that's accelerating, or maybe it's not accelerating, but the thing that you're interested in this particular problem. You want to take that object and represent it by drawing a little dot for your free body diagram. And then the rest of the free body diagram happens when you draw the forces that act on that object. So in other words, acting on your little dot that you drew. So drawing the forces means drawing arrows that represent force vectors. So they should have appropriate directions, and if you know them, they should have appropriate lengths. And the key to this step in drawing your free body diagram is just making sure that you only draw the forces that act on your object and not any forces that are exerted by your object. So sometimes that can be a little bit tricky. Okay, next step is going to be choosing a convenient coordinate system. So sometimes you'll want to use just the conventional coordinate system where your positive x direction points to the right and positive y points up. A lot of the times we'll be using that system. But sometimes when your object is moving, it's useful to align your coordinate system along the direction of motion. Or if it's not moving, sometimes it can be useful to align your coordinate system so that one of the coordinate directions, so either x or y, is aligned with a lot of your forces. So that can just simplify things when it comes to the next step, which is determining the x and y components of each of the forces acting on your object. Remember, we have to do that because to do a vector sum, you have to break things into x and y components. So we're always going to be looking for the x and y components of all the forces acting on our object. Once we have those, we can add together like components to determine the net force acting in the x direction and the net force acting in the y direction. And then the final step in these Newton's second law types of problems will be to set that net acceleration in the x direction, which you got by adding together all of the x components of all the forces acting on your object and setting that equal to the mass of your object times its acceleration in the x direction. And then you want to do a similar process for the net force in the y direction. Add up all the components of the forces, all the y components of the forces acting on your object, and set it equal to the mass of your object times its acceleration in the y direction. All right, let's go ahead and do a practice problem with free body diagrams and problem solving using Newton's second law. So here we want to hang a 0.2 kilogram picture frame using a wire, and you want the frame to balance equally between both sides of the wire so that the left and right sides of the wire both form 30-degree angles with the top of the frame. So here's our rough sketch of this situation up in the top right corner. Okay, and then we want to know what are the magnitudes of the forces along the wires that balance the picture. All right, so the first step would just be to draw a rough sketch. We already have it provided here, but I'm just going to add to that rough sketch all of the forces that I can think of in this situation. So the forces I'd be thinking of are the forces along the two parts of the wire that connect to the top of the frame. So I've called those F1 and F2. And then the unnamed force in this problem, which is something you're always going to want to think about, which is the force of gravity, or in other words, the weight of the frame. So the force of gravity we know always acts downward, so I would draw an FG acting downward here. All right, now our next step after we have our rough sketch is to draw our free body diagram. So you want to use a dot to represent your object. So here my object is my frame, so my little dot represents my frame. And then I want to draw in all the forces that act on that object, and I want to do a decent representation of those forces in terms of their angles and magnitudes. So here would be a case where I don't know the magnitudes of F1 and F2, so I just had to guess, but I do know that they're at 30-degree angles to the horizontal, so that I have drawn in. All right, and then I've also drawn in FG, which we know points down. Okay, so there's my free body diagram. We're good on that. Next step in terms of solving this problem using Newton's second law is going to be breaking all of our forces up into x and y components so that we can add the like components together and get the net force in the x direction on this object and the net force in the y direction on this object. So here we don't really have any of those special situations that I talked about that might make choosing a different coordinate system than the usual one more convenient. So we don't really have a way that we can align all of our forces with one coordinate, and we also don't have a moving object. So I just chose the conventional positive x points right and positive y points up here. Okay, so then our next step is going to be breaking all of our forces up into their x and y components respectively. Okay, so let's go ahead and do that. I'm going to start with the force of gravity, or in other words, the weight of my object. So looking at my chosen coordinate system here, I can see that the force of gravity is entirely in the y direction. It doesn't have any x components, and so Fgx is going to be 0. Fgy, we know it's pointing down, so that's the negative y direction. So I would say that it's minus m times g, where remember m is the mass of the frame and g is the acceleration due to gravity. Okay, so that's going to be it for the weight. So now let's look at what I called F1 here, which is the force along the wire that's pointing to the left. Okay, so I want to break that guy up into x and y components, so I would make a little right triangle where the legs of the right triangle are along x and y, and then I know that the force itself makes a 30-degree angle above the negative x-axis. Okay, so this angle right in here is going to be 30 degrees, and so then I can use my trig relations, my SOHCAHTOA relations, to write down that the x component of F1 is going to be minus because it's mostly pointing left and not right? So that's why I get a minus for the x direction. So it'd be minus F1 cosine of 30, and then F1y is pointing up, so it's positive, so I would just get a positive F1 sine of 30 degrees. Okay, now let's go ahead and do F2, which is the force along the other wire that's pointing to the right. So here again, there's a 30-degree angle between F2 and the horizontal. So if I were to think about making a little right triangle with legs that are along x and y, I would find that F2x is going to be F2 cosine of 30. This time it's positive because F2 is pointing to the right. All right, and then I would have F2y that's equal to F2 sine of 30. And again, it should be positive here because it's generally pointing up. All right, so those are my x and y components of the vectors, and so now to find the net force in the x direction and the net force in the y direction, I just have to add like components. So F net x is just going to be the x component of the weight plus the x component of force 1 plus the x component of force 2. The x component of the weight is 0, and so I end up with F net x is equal to minus F1 cosine 30 plus F2 cosine of 30. All right, now let's do F net y. So F net y is going to be Fgy plus F1y plus F2y. So in other words, just the y components of all the forces acting on my object. And then I can plug in each of these y components that I have written down. I get minus mg plus F1 sine 30 plus F2 sine of 30 degrees. All right, so now we're on to the last step, which is just to solve our problem using Newton's second law. Okay, so now to finish up this problem, we have to go back to the problem statement and remind ourselves about the acceleration of the picture frame. So our picture frame is at rest, it's balanced, right? It's not moving up or down, it's not moving left or right. And so since it has a constant velocity of 0, that means that it has an acceleration of 0 as well. And so constant velocity, even when the constant velocity is 0, always just means acceleration of 0. And so that means both a net x and a net y are going to be 0 here. All right, so we'll plug that in and use our Newton's second law relationship in the x and y directions to solve this problem. Okay, so here I've taken f net x, it's equal to m times a net x, and I just said a net x is going to be 0 since the frame is at rest, so I get 0. All right, so then I can use that with the relationship that I derived for f net x on the previous slide. So I say 0 is equal to the sum of the x components of all the forces acting on my object. All right, and so now I'm going to have two unknowns, f1 and f2, but I get a relationship between them. I just rearranged here. We get cosine 30 on both sides, which will cancel. And so here I can see that f1 must be equal to f2 in magnitude. All right, so let's go ahead and do our y components to figure out what that magnitude is. So we know f net y is equal to m times a net y. We said up above a net y is 0, right, because our frame is at rest, and so f net y must also be 0. Okay, so now we take that 0 and we set it equal to the sum of all the y components of the forces acting on our object. Okay, so I just plug that in from the previous slide, and then we can rearrange. Okay, so we get a little rearranging here, we simplify a little bit, and now I still have my two unknowns, f1 plus f2, but remember we know a relationship between those two unknowns. Specifically, the magnitude of f1 is equal to the magnitude of f2. And so what I can do here is I can replace this second force, this f2, I can just replace it with f1. I get f1 plus f1 in parentheses here, which is 2 times f1. Okay, and so now I only have one unknown, which is f1, and so we can just rearrange and solve here. And so when I did that, I got f1 was equal to 2 newtons, and then we know f2 has the same magnitude as f1, so it's also going to be 2 newtons. Okay, so we've done it, and we've solved our problem. Okay, so we're going to be continuing to work with Newton's second law and free body diagrams, but now we're also going to introduce Newton's third law of motion, which is sometimes referred to as the law of action and reaction. So the law tells us that for every force that acts on an object, this force is called an action force, the object will exert a reaction force, which acts on a different object, that's equal in magnitude and opposite in direction compared to the action force. All right, so that's a lot of words, but let's break it down a little bit. So first thing I see when I read that problem statement is that forces always come in pairs. So these forces are always coming in pairs. There's always an action force and a reaction force. We also see from this problem statement that those two forces, the forces in a pair, are going to act on different objects. So one will act on object 1, for example, in my drawing here, and the other will act on object 2. All right, we also see from this Newton's third law of motion that these pairs of forces will have equal magnitudes, but opposite directions. So mathematically, we could write down that if we have a force F12 that's exerted by object 1 on object 2, so that would be this top force here, then there will be an equal and opposite force, F21, that's exerted by object 2 on object 1. So we could write down that F21 is equal to minus F12. All right. So now there's two important points that I'd like to make note of here. So first of all, just because the forces are equal and opposite does not mean that the accelerations will be equal and opposite. And usually they won't be, right? Because we remember that the force on an object is equal to its mass times its acceleration, or in other words, the acceleration of the object is going to be the force, the net force, divided by the mass of the object. And so if your two objects that these two forces are acting on have different masses, then they'll have different accelerations. So a really good example to think about is the fact that the Earth is exerting the force of gravity on you, pulling you towards the Earth. So you must be exerting an equal and opposite reaction force on the Earth, pulling the Earth towards you. Okay, however, when you jump off the ground, the Earth pulls you back towards the ground and you accelerate towards the ground at a rate of 9.8 meters per second squared. Okay, however, when you jump off the Earth will also accelerate towards you. It's being pulled towards you, but because your mass is so small, that means that its acceleration towards you it's indetectable, right? So you can't tell that the Earth is also accelerating towards you when you jump off of it. All right, second point that I'd like to make here is because the action and reaction forces act on different objects, they won't cancel out. And so this is really important in terms of our free body diagrams that we talked about a little bit earlier. So remember, one of the key points I made in drawing those free body diagrams is that you only want to include forces that act on your object of interest. And so this is where things can get a little tricky because your object of interest is also going to be exerting reaction forces, but they'll be acting on other objects. So you don't want to include those in your free body diagrams because otherwise you'll just get things canceling out, and we know that those two forces don't actually cancel since they're not acting on the same thing. Okay, let's do a little practice problem here. So as a car accelerates, its engine acts to turn the wheels of the car, and which of the following best describes the force that causes the car to accelerate? Is it that the spinning tires exert a force on the road that push the car forward, or that the spinning tires exert a force on the road, which then exerts an equal and opposite force on the tires pushing the car forward? Okay, so to answer this question, we just have to remember that Newton's second law tells us that the net force acting on an object causes that object to accelerate. And so here, if we look at part A, the spinning tires exert a force on the road. And so that would cause the road to accelerate, not the car, right? So what actually causes the car to accelerate is the fact that when the car's tires exert a force on the road will exert an equal and opposite force back on the tires. So that will cause the car, it's really acting on the tires, but it also is acting on the car. So that force can cause the car to accelerate forward. Okay, so we want to be really careful then in terms of thinking about these action and reaction forces. Remember that it's only forces acting on a particular object that will cause it to accelerate. Okay, and so I would go ahead and pick answer B here. So there are many forces that we can talk about that come up as a result of Newton's third law. And so we're going to talk about two different classes of forces that are really action and reaction forces that come from Newton's third law. So first of all, we're going to talk about contact forces. Contact forces are just forces that are the results of objects touching each other. So a lot of the forces that we've been talking about so far have all been contact forces. So we'll just be doing few more examples in dealing with contact forces here. So for example, in the diagram, I have a person pushing on block 1. Block 1 will push back on the person, right, with an equal and opposite force. Both of those two forces would be contact forces. Here we can also see that blocks 1 and 2 are pushing, so block 1 would exert a force on block 2, and block 2 would exert a force back on block 1. Okay. The second type of force that we're going to be talking about is the normal force. So the normal force is the force perpendicular to any surface that keeps an object from sinking through. So here I have a box on an inclined plane, for example, and so the box, remember, it has a weight. So it's going to have gravity pulling down on it, which is going to cause the box to exert a force on the plane. But it doesn't sink through the plane because there must be another force pushing up on the box that prevents it from sinking through the plane. And so that force is the normal force. Here you can see I have it drawn in and it is acting perpendicular to the ramp. And then because the normal force is the force of the ramp acting on the box, it's going to be the result of the fact that the box will have a normal force acting down on the ramp. So those are going to be action-reaction pairs here. Okay, so let's talk a little bit more about contact forces. So remember, these are just the result of objects touching each other. They're always going to come in action and reaction pairs, and these are probably the most common types of forces. So several examples of contact forces. Anytime you have two objects touching and pushing on each other, you're going to get a contact force. So earlier in the lecture, we talked about the force of the tires of a car on the road, and we talked about the resulting reaction force of the road on the tires. Those are both contact forces. Those two things are touching, and they come in an action-reaction pair. We'll see lots of examples of contact forces. Okay, and so then my big note on contact forces, and really this is going to be true for any forces as you're working through these Newton's second law types of problems, it's really important to just think about what forces are acting on your object of interest. So you have to be careful that you don't include any forces that your object is exerting on other objects when you're thinking about the acceleration of your object of interest. So it's really important to just distinguish only the forces acting on a particular object will cause that object to accelerate. Okay, so it's something that will get easier with some practice. All right, so now let's talk a little bit more about the normal force. So in thinking about the normal force, I just want you to consider the fact that right now gravity is acting on you, right? So the force of gravity is pulling you down towards the center of the earth. But you're sitting maybe in a chair, something like that. So you're not actually accelerating down, right? So your net acceleration in the y direction, it's not the acceleration due to gravity, unless you're in free fall right now, which I doubt. So it's not going to be the acceleration due to gravity. You're going to be at rest in the y direction, so the net acceleration in the y direction should be 0. So for that to happen, we know that the net force acting on you in the y direction must also be 0. So in other words, there must be some other force that's acting on you right now to balance out gravity as you sit in your chair. Okay, so let's talk about that force. So here we know that the weight of your body is pulling you downwards, right? And so as you sit in your chair, that means that you're going to exert a force on the chair, contact force, because you're touching it. So you're going to exert a force on the chair that's exactly equal to your weight. Then from Newton's third law, we know that there's an action-reaction pair here, so your chair must exert an equal and opposite force back on you. Okay, and so that's the force then that's balancing out your weight pulling you down. And that is also then the force that we call the normal force, and it's really going to be what prevents you from just sinking through your chair since gravity is pulling you down. All right, so let's talk a little bit more about this normal force. Like I just mentioned, it's always going to be what prevents you from sinking through the surface that you're sitting on, any object is sitting on. And so in general, we could say then that the normal force is always a force perpendicular to any surface that keeps an object sitting on that surface from sinking through. So where does it come from? Well, it's really due to the interaction between atoms in a solid that will help a solid maintain its shape. So the solid that you're sitting on, the solid surface, it doesn't want objects to sink into it. So those atoms, they want to prevent other atoms from coming into their surface. And so what that means is that when an object is set on a solid surface, that object will exert a force on that solid surface, and that force will cause the solid surface to compress a little bit, so it will cause it to accelerate, although most of the time that's an imperceptible acceleration. Then that surface is going to exert a force back up on the object to oppose that compression, and that object, or that force, is called the normal force. Okay, so now let's go ahead and talk a little bit more about how we can actually determine what the magnitude of that normal force is going to be. So really the normal force, remember, it's what keeps you from sinking through a surface, and so that means that it's going to be the force that balances Newton's second law for an object sitting on a surface, and it specifically is going to balance Newton's second law for the direction that's perpendicular to the surface. So here, if I were to think about the net force perpendicular to a surface, which I'm calling F net perp, I would want to set that equal to the mass of the object sitting on the surface multiplied by the acceleration of the object in the direction perpendicular to the surface. So that's going to be my A net perp here. Okay, and so then the normal force is going to be the force that perfectly balances that equation. Okay, and so then we're going to need to think about what is the net force acting on an object perpendicular to some surface. So to do that, we can think about some forces that may have non-zero components perpendicular to a surface. So this F net perp may include things like weight, or at least a component of the weight. It's always going to include the normal force because we know the normal force always acts perpendicular to a surface. So that's always going to be included in F net perp. And then there might also be some other applied forces that could be acting or could have components acting in the direction perpendicular to a surface. And so what that means is that you could end up with a normal force that's greater than, less than, or equal to the weight of the object sitting on the surface. Okay, so let's look at some examples of this. Okay, so each of the following examples, I have a box sitting on a surface, and I'm going to assume that the box is at rest, which means that its net acceleration in the direction perpendicular to the surface is 0, and so the net force in the direction perpendicular to the surface is also going to be 0. So this is the net force acting on the box. Okay, so here's my first example. The box is sitting on a horizontal surface, so the direction perpendicular to the surface would be the conventional y direction. So now if I want to think about the sum of the forces acting in the direction perpendicular to the surface, well, I would have the force of the gravity pulling down on the box, so that's going to be in the minus y direction, so I would use minus mg for that guy. And then I would also have the normal force, which we know is always perpendicular to the surface. Here would be pushing up on the block, so I would do plus n. All right, so this is going to be the net force acting on my block in the direction perpendicular to the surface. We know that that net force has to be equal to 0 since it's not accelerating up or down here. And so then I would see that in this particular case, the normal force acting on the box is exactly equal to the weight of the box pulling down. Okay, next example here is a little bit trickier. We have the same setup except there's one more force. So now we have an additional applied force which is pushing generally downwards on the box. And so then if we were to think about the net force in the direction perpendicular to the surface, which would be the y direction, then we could think about, okay, we would want still the weight pulling down, so that would be minus mg. Then there's going to be a y component of this applied force that's pulling generally downwards, right? So I would do minus the y component of that applied force, plus then the normal force pushing up on the box. And so then we can see that the result is that the normal force would be equal to the weight of the box plus that y component of the applied force. So it has to balance both of those two things to prevent the box from sinking through the surface. That means that the normal force is going to be bigger than just the weight of the box in this case. All right, in our next example, we have another applied force, but this time instead of pushing down on the box, it's going to be pulling up a little bit on the box. Not enough to lift the box, just a little bit. Okay, so the net acceleration in the direction perpendicular to the surface is still 0, but we do have this additional applied force pulling with a component that's going to point upwards. Then if I were to think about the net force perpendicular to the surface, or in other words, in the y direction, I would still have the weight pulling down, so minus mg. Now the y component of this applied force would be generally pointing up. So here I would say that that y component is going to be plus F applied y. All right, and then we know the normal force is also going to be pushing up on the box from the surface. And so then I would also have my normal force in this equation. Okay, and so then we can see here that because the net force on the box in the y direction or in the direction perpendicular to the surface has to be 0 because it's not accelerating, then we can see that the normal force in this case is going to be the weight minus the applied force. So because you're pulling up a little bit on the box, the normal force has to do less work to prevent that box from sinking through the surface. And so that's why in this case the normal force would be less than the weight of the box. All right, there's one more situation that we're going to talk about in detail in just a few slides here, and that's the situation where you have a box on a tilted surface, and we'll be talking about that in a little bit, but it turns out that in this case the normal force is also going to be less than the weight of the box. Okay, let's do a quick practice problem here. When you stand on flat ground with weight Fg, we want to know what is the normal force of the ground acting on you. Okay, so to answer this question, I would think about drawing a free body diagram here. So I would use a dot that represents you. You're standing on a flat horizontal surface, which means that the direction that's perpendicular to the surface is going to be the conventional y direction here. Okay, and then I know that there's going to be two forces acting on you, your weight pulling directly down, and the normal force, which is perpendicular to that flat surface of the ground. So in other words, the normal force is going to be acting in the positive y direction. Then I know that the magnitude of that normal force is going to be exactly what's needed to balance the equation that the net force in the direction perpendicular to the ground, so in other words in the y direction, is equal to my mass times my acceleration in that direction perpendicular to the ground. Okay, and so in this case then I could think about what is the net force in the direction perpendicular to the ground, or in other words F net y here. F net y is going to be the normal force, which is acting upwards, so I would use positive n, minus your weight pulling down, so minus Fg. Okay, so that's going to be the sum of the y components of all the forces acting on you. Then remember that F net y is also equal to mass times acceleration in the y direction. Here you're standing on the flat ground, which means you're at rest on the flat ground, so your acceleration in the y direction is 0, and that's why then we get F net is also equal to 0 in the y direction. Okay, so now we can combine these two equations and solve for the normal force. The magnitude of the normal force is just exactly equal to your weight, and we already said that the direction of the normal force is going to be up, so opposite to your weight, and that's because it's the floor pushing up on you to prevent you from sinking through. Okay, so I would go ahead and pick answer A here. Okay, so now we want to go back and think about that last case on the slide where we were talking about how you could determine the normal force, and that's the case where you have an object sitting on a tilted surface. So far we've mostly been dealing with objects sitting on flat surfaces, but now we want to think about what happens when you have an object sitting on a tilted surface. Okay, so what happens in this case? Then we know that the normal force is always acting perpendicular to the surface. So that means that the normal force is no longer in like the conventional y direction. It would be perpendicular to that angled surface. Okay, but we know that the weight is always going to be pulling directly down. So that's the force of gravity pulling down on the object. And so that's going to continue to be in the negative conventional y direction. So then we can see here that Fg, your weight, and the normal force acting on the object, they're no longer going to be parallel to each other. And so then it turns out that normally when we have an object sitting on a tilted surface, a lot of the times the object is going to be moving along that tilted surface. And remember we said that it's usually convenient when you have an object that's moving in a particular direction to choose that direction to be either the X or Y direction. And so what we can do here, what's usually convenient to do here, is to choose the direction that corresponds to the incline of your surface that the object is sitting on. We usually want to choose that direction to be the X direction, so parallel to the surface, and then perpendicular to that surface, we usually choose to be the Y direction. So here you can see that your normal force, which is always perpendicular to the surface, now your normal force is going to be pointing in the Y direction, but you see that Fg is no longer going to be in the Y direction since it's still pointing directly down. Okay, so then what does it mean for us that Fg is no longer all along the Y direction? Well, it means that when we're thinking about doing Newton's second law, remember we're always going to have to break all the forces acting on the object, so here the box, up into their X and Y components. Now that means that Fg is no longer just going to be in the Y direction. So we're actually going to have to find its X and Y components. Okay, so then the X component of Fg will be parallel to the inclined surface. Fgy is going to be perpendicular to that surface. So we want to draw in a little right triangle so that Fgy is perpendicular to the surface that the box is sitting on, and then Fgx is parallel to that surface. So I've drawn in this little right triangle here, and then if we want to relate the weight to its X and Y components, we're going to need to find this angle inside here. So that's our goal. All right, so how do we do that? First of all, I look at this little triangle here that's formed by the horizontal and my inclined plane, and then a vertical line. Okay, so if I were to look at that triangle, then I know that the angles inside a triangle have to add up to 180 degrees, and so I have a right angle between my horizontal and vertical legs. I have the angle theta between the incline and the horizontal, and so that leaves me with an angle that's represented by these pink dashed lines in here of 90 degrees minus theta. All right, and so then we can also see that we have another right angle here between the surface and the Y component of my Fg. So I have a right angle in there, which is going to be 90 degrees. Then you can see that part of that angle is made up by this 90 degrees minus theta, and part of it is made up by this angle of interest here. So that's the angle that we're looking for. All right, so the total angle has to be 90. 90 has to be equal to 90 minus theta plus the angle that we're looking for, and so that means the angle that we're looking for is going to be theta. All right, so this is one of the few things that I would say just go ahead and memorize in this class. The angle that's in between the normal direction, so the direction that's perpendicular to the surface, and your weight component, your weight force here, acting on the box, is always going to be theta. So you can always go ahead and draw in the angle between the Y component of Fg and Fg as just the angle theta of the incline of the surface. Okay, and so now that we know that the angle in between Fg and Fgy is theta, we can use trig to find out what the Y component of Fg is and what the X component of that weight is. And so specifically here we can see that using our SOHCAHTOA relationships, cosine is going to correspond to Fgy over Fg here, and sine is going to correspond to the opposite, which is Fgx divided by Fg. So that is opposite of normal, and that's just because of the way that the angle theta is defined here. So you'll always want to go back to those trig relationships. All right, so then we can rearrange those relationships and write down that Fgy, it's going to be minus Fg cosine theta because it's pointing in the negative Y direction. Then we know that Fgx is going to be minus Fg sine of theta. Again, it's going to be negative because it's pointing generally down the ramp, which means it's in the negative X direction. All right, and then last thing to note here is Fg is just the magnitude of the weight, and so that's going to correspond to m times g, where m is the mass of the box on the surface in this case. Okay, so then once you have those components, then you'll be able to use those components to find F net x and F net y for the box, and then you'll be able to apply Newton's second law along the x direction, which is parallel to the inclined surface, and along the y direction, which would be perpendicular to that incline. Okay, so let's go ahead and do a practice problem here. We have an inclined surface that has an elevation of theta relative to the horizontal axis, and we want to know which of the other labeled angles in this diagram corresponds to the angle theta. Okay, so we just saw in the last slide that the angle B here does correspond to the angle theta. The angle A does not, so that's going to be 90 degrees minus theta, and that's actually the same as angle C down at the bottom here. So C and A, because you have a line that's bisecting parallel lines, so C and A are equal. Those are both 90 degrees minus theta. B is the one that's going to be equal to the angle theta, the angle of the incline here. So I would go ahead and pick answer B. Okay, so we have one last topic to talk about for today, and that's this idea that a lot of the times when we have an object sitting on a surface, usually the net force on that object in the direction perpendicular to the surface is 0. In other words, the object is not accelerating in the direction perpendicular to the surface that it's sitting on. So a lot of the times this is going to be true, but sometimes it's non-zero. So sometimes the net acceleration in that direction perpendicular to the surface is non-zero. The classic example would be when you're riding in an elevator or on a roller coaster. Okay, so here let's talk about what happens when you're in an elevator. So you've probably noticed that sometimes you feel light. So specifically when the elevator is going downwards, you feel light. And when the elevator is going up, you feel extra heavy, right? And so why does that happen? Well, it turns out that the sensation that you have of weight, so feeling of weight that you can perceive, it really comes from the normal force pushing up on your feet. So it's the normal force of the surface that you're standing on pushing up on you. That gives you your perception of your weight. And so here when we think about you're in an elevator and it's going downwards, if it's accelerating downwards, you feel light because the normal force is reduced compared to your normal weight. All right, then similarly, if you have an elevator that's accelerating upwards, it turns out that the normal force will be greater than your normal weight, and so that's why you feel heavy. All right, so let's take a look at where this comes from mathematically. So let's go ahead and think about an elevator again, and we're going to let the conventional upwards direction be the positive y direction. All right, so then if we want to think about the net force and acceleration in the direction that's perpendicular to the surface, so the floor of the elevator, then we're going to want to think about the y direction. So we're going to think F net y is equal to the mass of you standing in the elevator multiplied by your net acceleration in the y direction. All right, then we know that that net force in the y direction is going to be the sum of all of the forces acting on you in the y direction. So we know that the floor is pushing up on you, so the normal force is going to be acting up on you to prevent you from falling through. And then we also know that weight, your gravity is always pulling you down. So we have minus Fg. Okay. And so then we can go ahead and use this equation. We set n minus Fg equal to your mass times your net acceleration in the y direction, and we can solve for the normal force. And so then we see that the normal force is going to be equal to your mass multiplied by your net acceleration in the y direction plus the acceleration due to gravity. Okay, so let's look at two separate cases here. So the first case would be when you're accelerating downwards. So this would be the top case where you feel light in the elevator because it's accelerating downward. So why is it that you feel light? Well, if we look at this equation in the box here, we have m times a net y plus g equal to our normal force. In this case, because you're accelerating down, the net acceleration in the y direction is negative. And so that means that your normal force is going to be m multiplied by minus a net y plus g, right? So minus some number plus g. So in other words, this term in parentheses here, it's going to end up being smaller than g. You're subtracting something off from g. And so then that means that the normal force is going to be something less than m times g. In other words, it's going to be less than your weight. You can also think about this by thinking about drawing a free body diagram here. If you're accelerating downward, the net acceleration is downward, then you know that F net y is going to be pointing down. So you would think about having F net y pointing down, Fg pointing down, and the normal force, remember, is exactly whatever balances the sum of F net y is equal to Fg plus the normal force. And so then you can see here that the normal force will end up being something smaller than your weight. So either analysis would work. All right, let's look at the second case here, which is the case where you're accelerating up, and this is the case where you feel heavy. So in other words, your normal force, the normal force acting on you is going to be greater than your weight. So in this case, the acceleration, your net acceleration in the y direction is positive. So when you do a net y plus g, you're going to get something bigger than g. So that term in parentheses will be bigger than g, and so m times whatever is in parentheses is going to be bigger than m times g. In other words, your normal force is going to be greater than your weight. Okay, we can also see this by again thinking about drawing in a free body diagram. Here the net acceleration is in the upwards direction, so F net y is going to be pointing up. we know that f net y has to be equal to the vector sum of fg and n. And so then if you were to do a vector sum here, you would find that n must point upwards and it must be bigger than fg. Okay. All right, and so then one last note here is just that sometimes the normal force in these cases where we are talking about your sensation of weight, remember the sensation of weight comes from the normal force, and so sometimes the normal force is referred to as your apparent weight. And so if ever you're asked to find the apparent weight, that just means look for the normal force. Okay. All right, so let's talk a little bit more about this apparent weight, or in other words, the normal force, and let's talk about the idea of weightlessness. So feeling weightless. So if you were to feel weightless, that means that the normal force acting on you is 0, right? So your sensation of the forces acting on you is 0. Okay, so what condition is required for the normal force to be 0? Well, if I were to plug in 0 here, then we can see that we would want to get a net y plus g equal to 0, or in other words, the net acceleration in the y direction needs to be minus g. So when is the net acceleration in the y direction minus g? That's actually when you're in free fall. Okay, so for example, you will feel weightless if you're in free fall. So classic example is actually NASA uses this effect to train astronauts for going to space. They use this airplane which goes up really high and then it dives down really quickly so that the astronauts inside experience weightlessness. They experience an acceleration of minus g, and so they feel weightless on the way down. Apparently it's a pretty rough ride. It's affectionately referred to as the vomit comet. So kind of fun. There's lots of videos online if you're interested in seeing it. It turns out the weightlessness part of it only lasts about 30 seconds while it just accelerates straight down, but pretty cool. All right, let's wrap up for today with one quick practice problem. You're riding in an elevator that's rising at constant speed, and we want to know what is your apparent weight, which remember just means what is the normal force acting on you. Okay, so there's really a key piece of information that will help you solve this problem, which is that the elevator is rising at constant speed, right? So constant speed, it's going in the upwards direction. We can assume it's going in the same direction all the time. So that means it has constant velocity. And remember, acceleration is related to change in velocity. So if the velocity isn't changing, your acceleration is 0. So here, if we let the upwards direction be the conventional y direction, then we know that the net acceleration of this elevator in the y direction is going to be 0. Then, since f net y is going to be equal to mass times net acceleration in the y direction, f net y is also going to be 0 here. We know that f net y is also equal to the sum of all of the y components of the forces acting on you. Here you have the normal force pushing up and gravity pushing down, so we get n minus fg. We set that equal to 0, and then we can see that the normal force in this case, where the acceleration is 0, is just going to be exactly equal to your weight. Okay, so I would go ahead and pick answer B. All right, so that wraps it up for today. We're going to be doing a lot of practice problems with all of this in class, and I will see you guys then.